So, first of all, why we are doing this next experiment? So I will start with an introduction on neutrino. The neutrino was hypothesized for the first time as a so-called desperate remedy to save the energy momentum conservation. Indeed, during in the beta decay, it was the only particle observed was the electron. So it was thought to be a two-body decay, and the signature expected um, was just a monochromatic energy emission for this electron. While instead, what was observed was the typical beta spectrum that we know now, but this could not be observed, could not be explained as a single body decay. So it was assumed, Pauli assumed that another particle was emitted in this decay. So effectively, the beta decay was a three-body decay, and in this way we could explain everything. However, Pauli said a terrible thing, so to theorize a particle that cannot be detected, since according to the calculation, this particle should have a mass which is below 0.01 times the proton mass, and a penetration power which was 10 times higher than the one of a gamma. At the time, with the detection technique of the time, this was thought to be unthinkable. And in reality, we know now that the mass of this neutrino is 10 to the minus 9 times the mass of the proton, with a cross-section which is more than 30 order of magnitude smaller with respect to the one of a gamma. So how do we detect this particle? We need a lot of neutrino, and we need a lot of target. So a very big detector mass. And was how the neutrino was detected. So if the beta decay is possible, also the inverse reaction in which a proton interact with a neutrino and produce a neutron and a positron was possible. And as a source, it was thought to use a nuclear power plant with the 10 to the 16, 10 to the 19 fission per second, and a big detector made by a huge tank of water with cadmium dichloride to detect neutrons and surrounded by scintillator with photomultiplier. So what they did, they prepared this experiment. The concept was that neutrino interact with proton, producing a neutron and a positron. The positron then interact with an electron of the water, producing very typical signature of two 511 Keith gammas detected in coincidence. The neutron then is captured by a 108 cadmium, producing a 109 cadmium and several gammas. Thanks to this very strong technique, thanks to the coincidence, have a very good background suppression, they send a telegram to Pauli saying that they have discovered the neutrino, and they measured the cross-section of 10 to the minus 44 centimeters square. Going on with the story of the neutrino, after the solar neutrino problem at the Homestake experiment, it was realized that there are different flavors of neutrino, and these neutrino can oscillate among each other, so they can change flavor along their path, giving rise to a non-null probability that a neutrino produced with a given flavor can interact then with another flavor. And what is the key point of this observation? This observation confirmed that neutrino have a mass. So these oscillations are only possible if the neutrino have a difference in mass, and so this must confirm that this particle must have a mass. Otherwise, they could have thought to be massless for how light they are. And now this gives rise to a very big problem, which is why the neutrino are so light. The limit for the mass of the neutrino is 0.45 electron volt, which is unnaturally small compared with the other standard model particles, which are all years. So additionally, there is not a mechanism in the standard model that can give mass to neutrinos. So in principle, in the standard model, they are massless. So we need something beyond the standard model to give mass of the neutrino. And we arrive here to the direct neutrino versus the Majorana neutrino. To give mass to a direct neutrino, so in which the neutrino and antineutrino are two different particles, you should build the electron mass term as for a fermion, and then give mass to it through the Yukawa coupling. However, what happened that to do this, we need to add to a standard model a sterile right-handed neutrino with all the quantum number equal to 0, so this particle in principle could not interact. And we need a natural value of the Yukawa coupling, which is fine-tuned to less than 10 to the minus 13. This value is a bit unnatural. However, if you assume a Majorana neutrino, we can hypothesize the presence of a sterile right-handed very heavy neutrino, for which we have this heavy neutrino with a given mass, and our neutrino which have a mass which is inversely proportional to the heavy neutrino. So we can explain why the neutrino mass is so small under the Majorana hypothesis. Hypothesize the presence of a very heavy neutrino with a very big mass. So we should solve the problem of the naturalness, and moreover, since this a Majorana neutrino violates the electron number conservation, while the B minus L symmetry is preserved, so it means that B, the barium number, must also be violated, and this would explain also the matter-antimatter asymmetry through the leptogenesis. So we solve the leptogenesis under a Majorana neutrino hypothesis. We solve the leptogenesis. And we can also explain why the neutrino has such a small mass. Okay, now let's come to the double beta decay. The double beta decay represents a unique laboratory to test the Majorana nature of the neutrino. Indeed, when this happens sometimes when a nucleus, like the xenon 136, for example, could undergo beta decay to 136 cesium from the point of view of the number of protons and instability. However, this transition is forbidden since the 136 cesium is at an atomic energy level which is higher than the xenon. So this reaction cannot happen, but the 136 xenon can undergo double beta decay twice directly to the 136 barium. This is why the double beta decay happened. And what happened? It happened that this is the standard Feynman diagram of the two neutrino double beta decay. But if neutrino and antineutrino are the same particle, this particle can instead act as a mediator and give rise to the emission of two neutrinos with two electrons without the neutrinos. So this is, of course, extremely rare since it's a second-order weak interaction process. And additionally, here it's helicity suppressed since you have to change the helicity to the neutrino for this process to happen. Well, how rare is this process? Here is the amplitude. We have the phase space, which is pretty big. We have the nuclear matrix element, which is also order 1. However, we have the effective neutrino mass, which is very small, squared. So this we know. So this is the main problem, that we have the Majorana neutrino mass squared. So the current limit of the half-life is set to more than 10 to the 26 years. So we need a lot of time to observe this process, or we need a lot of mass. Okay, regarding the energy and topological signature, what we expect is to have the typical two neutrino double beta decay spectrum, while with the zero neutrino case, we expect the electron to have an energy which is a peak at the so-called Q beta value. The Q beta value is the energy at which the total energy of the reaction. So in absence of the two neutrino carrying out part of the energy, all the electrons are emitted monochromatically at the Q beta energy. However, this detector, this decay has also a very clear topological signature, which consists of two electrons produced more or less back to back, with a Bragg peak at the extremity. So detectors with tracking capabilities can access to this feature. Among the search strategy, with in the background case scenario and the background the free limit, the values of the neutrino mass are accessible, scales in this way with the mass of the target and the time, which are the key parameter. As you can see in a background case scenario, you have the sensitivity to the mass, to the neutrino mass, which scaled as 1/t to the 1/4, while instead in the background free limit you have the sensitivity scaling simply as one of the square root of the time. So given all this term, which enter in play also the energy resolution, the background counts, and the detector efficiency, we can say that the search strategy can go in different way. The first one is rely on an excellent energy resolution and a very low background, as it's done with the crystal, or rely in a very good background rejection and a good energy resolution, as it's done, can be done, for example, searching for this two blob signature, or better, go towards the background free limit. So towards the background free limit means going from this to this with a sensitivity that goes as one of the over the square root of the time, and we will see it later with the barium tagging technology. So here comes next electroluminescence time projection chamber filled with high pressure xenon. The pressure and the xenon 136 enrichment can be changed. When a particle interacts in the gas, it produces a primary scintillation light, and this light is recorded. Then the electron drifts towards the anode, and while crossing the electroluminescence region, the electrons are amplified. They excitate the xenon gas, and this gas produces light. This light is recorded both by the PMTs, which record also the S1, giving rise to a waveform which is proportional to the amount of charge density reaching the electroluminescence region. And there is also a tracking plane made by silicon photomultipliers that also sample the track arriving, the electron arriving in time, giving us the opportunity to record also a three-dimensional three-dimensional information of the track with the local energy, with the additional information of the local energy release in the track. Moreover, combining knowing the drift velocity, we can use the S1, S2 time difference to also infer the absolute Z of the track. The next experiment started with the prototypes. The first prototypes in 2010 with 1 kilogram of xenon. It moved then with the next white prototype with 5 kilogram of xenon, and we are currently with the next 100 experiment at Canfranc National Laboratory, and looking forward for the 1 ton scale experiment, to which we will start to project it in 2027. The next experiment has members in different countries: Germany, England, Spain, Portugal, and US, from more than 10 different universities. And Germany, yeah, not Poland. No one in Poland is doing next, right? Okay. And the detector now, the next 100 experiment, as well as the next white experiment, are hosted in Laboratori Nazionali di Laboratorio Sotterraneo de Canfranc, while here is where the TPC is in the very north part of the Spain, at the border with France. Okay, this is the next white. Let's start with the next white. The time projection chamber had, as I said before, 5 kilogram of active region with 50 centimeter, with a 50 centimeter drift length. It operated up to 20 bar pressure. here is here is the cathode and the energy plane with the photomultiplier that you can see here, while on the other side there was the tracking plane, which you can see here. Here there is a picture of the field cage, and later I will show you more in detail these the different components used in the next 100 experiment. Okay, the main goal of the experiment was to measure the energy resolution, to infer the energy resolution at the thallium peak, and perform a measurement of the two neutrino double beta decay half-life. We managed to keep the energy using different calibration sources. We have calibrated the detector, and we managed to demonstrate that we have an energy resolution which is less than 1% of width of maximum at the beta beta. Here there is the spectrum of the krypton, cesium, with 1.45% of the width of maximum energy resolution. And here there is the thallium peak and 2.6 MeV with an energy resolution of 0.91% full width of maximum. With the next white experiment, we also tested the Richardson-Lucid convolution. So when we have a track, of course, inside the detector, the primary electron produced drift towards, while drifting towards the anode, they diffuse a lot. So at the end, this is this is the track after once we add the diffusion effect. This is the track once we add the CPM response. However, the diffusion can be studied, in particular can be studied with the 83 metastable krypton events, which are point like the position of 40 MeV. We can use this krypton to characterize the so-called point spread function, so how much the track diffuse at a given coordinate. And thanks to this Richardson-Lucid convolution, we can use the point spread function measured with the krypton to deconvolve the diffusion effect. And after the diffusion effect, this is what we get. Then, studying the single blob, double blob characterization, as I showed you before, a double beta decay is expected to have two blobs at the extremity, while a background event consisting of a single electron is expected to have only one blob. This is the signal efficiency versus background rejection that we obtained using this Richardson-Lucid convolution. So you can see that even with a 60% signal efficiency, we reach more than, with this technique of the double blob, we reach more than 95% of background rejection, which is very good. Do you have questions? No. Okay, I thought you. Okay, then always with next white, we managed to make a measurement of the two neutrino double beta decay to measure the half-life. We did it in two ways. The first one was a background model dependent analysis. So we estimated all the background and we measured the contribution of the double beta decay of the xenon 136. Or we can do a unique thing that only Next can do, which is take data with a rich xenon enriched in xenon 136, and then take data with the xenon depleted in xenon 136. With this, we can perform directly a background subtraction, beam by beam background subtraction, and this is what we got. And this is the double beta decay subtracted spectrum, and from here we measured an half-life which is 2.34 10 to the 21 years for the two neutrino double beta decay. Of course, it's not competitive since it was done with only 5 kilograms of xenon.
So can I ask a question?
Yes, sir.
So how do you know how much of enrichment happened, or
we have these very well characterized. We have done mass spectrometry analysis of the xenon, so we have the exact composition of the. I don't have it here in the presentation. but we have exactly the spectrum with abundances of the different elements.
So you do sampling from the gas for this?
Yeah. We have done a sampling from the two gas. I didn't participate directly, but we have both the xenon enriched and depleted, characterized with all the isotopes that all the different isotopic abundance inside. Okay, this was also beyond the XY detector, but as a proof of principle, what we did is to perform also a double beta decay, neutrinoless double beta decay searches, again with the background dependent model and with the background subtraction. The results, which are reported here, are not so competitive, but in principle, they served as a proof of principle for the future analysis. And here, as you can see, with the background subtraction, we obtain something which is more or less a factor 2 better than the other result. Okay, next 100 now. The detector, next 100, started to operate in May 2024 at 4 bar. We have concluded the commissioning and calibration run. And also we have concluded the low background run at 4 bar, which is still under analysis. And the operation at 10 bar for neutrinoless double beta decay should start soon. The detector has on one side 60 PMTs. It has one veto and a drift field with 100 centimeter of diameter and 118 centimeter drift. And in the tracking plane, it has 3,584 CPM. It has also a LED shielding around, and it can host up to 100 kilogram of xenon at 15 bar. The main goal of the detector is to demonstrate that we can keep a resolution below 1% full width of maximum at 2 beta beta, improve the precision of the two neutrino double beta decay measurement, half-life measurement, and perform competitive search of the neutrinoless double beta decay, with which we should reach a limit of around 10 to the 26 sensitivity at 90% confidence limit after 3 years. Additionally, the plan is to demonstrate the scalability towards the ton scale. These are some pictures of NEXT. This is the interior of the vessel where the CPM plane is hosted. This is the internal copper shield, and this is a picture of the vessel. Other things, this is the field cage and the detail of the electroluminescence region with this hexagonal pattern. On the left also, there is a picture of a CPM board with the CPM coated with the TPB, which will be placed here within front a mask of Teflon. Also, it is coated with the TPB. And here there are the PMT details of the PMT windows, so the window of the PMT. Okay, regarding the detector commissioning, we used alpha particles for the commissioning to measure in particular electron lifetime, light yield, and drift properties. We measured an excellent electron lifetime, which quantify how the electrons are absorbed during the drift, and we measured a lifetime of more than 40 milliseconds, which is much more than the maximum drift time of 1 millisecond. Additionally, thanks to the alpha peak that we have observed in the energy distribution, we showed less than 1.1% LED variation in 24 hours, and in 3 months a LED variation of less than 1%. Sorry, I checked the time. Less than 1% in 3 months. We measured also a diffusion, and at the end drift velocity compatible with Mach bolts. Now, one key point of the detector response is that there is a strong geometric dependence on the interaction, so we must correct it. As you can see from the krypton map, there is a stronger radial response going from the center towards the border. So what we can do is to use the krypton point-like energy deposition, and with this map we build With this decay, we build a three-dimensional map of the local response, which can be used to correct the energy of the krypton at every interaction. So this is, for example, an uncorrected krypton spectrum. Once we correct it with the map, this is the new corrected spectrum that we get. This demonstrates a good energy resolution at low energy, at the krypton energy, plus it demonstrates the effectiveness of this way of correcting. The three-dimensional map is done in the whole detector volume.
So what pattern we see here?
This pattern,
Yeah.
This pattern are the dice boards because
So between dice board, you
yes,
some
There's results in the
yeah, if I have a picture, yeah, between one dice and another, there is a very small gap. So probably that is the pattern, that if the krypton is produced in the space within the dice, some light is lost. The effect, of course, is also lost going at tight Z. With a bigger diffusion, this effect is less relevant. Okay, then regarding the high energy track, of course, we cannot correct it if there was a krypton with a barycenter, since they have a complicated extension in Z. And what we do is to calculate the energy of each in each slice of the PMT waveform. We share this energy proportionally to the charge, which is at every CPM, silicon photomultiplier heat. So we share this energy proportionally to the charge. Then we correct each heat of the track with the krypton map, and then we recalculate the energy. By doing this, we managed to demonstrate an energy resolution of 0.9% full width of maximum at the thallium energy that extrapolates to less than 1% at the double beta decay energy. There are topology studies which are in progress. This is a double electron candidate, while this is a single electron candidate, and also the background study regarding this data that we have acquired at 4 bar are in progress and will come out soon with results on these two topics. Regarding now the upgrade of Next 100, since the PMT technology is challenging to scale, especially if you work in high pressure environment, what we are thinking is to see if a fiber barrel technology is available for. We can use this technology instead of the PMTs for the Next 100. So we are now, in principle, this technology should have an high enough efficiency, would also lead to improve the radioactive budget, since we don't have anymore the PMT, and we will not need anymore for an energy plane. So in principle, we could move to a technology with a common double side TPC with common cathodes. Additionally, these fibers, as well as the CPM, are very easily to find commercially. So we don't need to continue to rely on the PMTs. So this is the plans for the future of Next 100. We want to replace the plane with the photomultiplier. We want to cancel it and instead surround the barrel of the detector with scintillating fibers that then will be collected to a silicon photomultiplier. And we will use these for detection of the primary scintillation light and secondary scintillation light, so for the energy measurement. So, for the energy measurement, yes. And before scaling to next HD, we have to validate the technology, and we are now building this HD demonstrator, which is a small detector that we have. We are instrumenting it with this fiber barrel technology. And we are also experimenting the technique of putting a common cathode, a symmetric detector with a common cathode and two chambers. One thing, of course, is that the CPM must be cooled to reduce the dark noise, since with an interaction of krypton as primary scintillation light is expected to give us around 20 photoelectrons. So we have to constrain the dark noise. This detector is currently being assembled at the IPC. Here you can see the panels with the fibers coated with the TPB. This is the field cage with the panel mounted inside, and here on the bottom you can see the tracking plane, picture of the field cage, and here is the back view of the CPM plane with all the fibers here, which are then collected into an holder to which the CPMs will be connected. Okay, other technology for the future of next. We already spoke about the fiber barrel detector. We will see more in detail the barium tagging demonstrator. Other plans are to build a denser silicon photomultiplier plane for better granularity, new ASIC design, or development of metal lens to improve the light collection efficiency. Towards the future of the next HD, the tone scale detector, which will consist of a symmetric TPC with central cathode, two chambers with the barrels covered with these panels with the fibers. It will feature a denser CPM plane, and there are possibility for the use of gas additive like helium-4 to reduce the diffusions, and helium-3 doping to reduce the cosmogenic 137 xenon. Okay, now we say that for this research we can rely on a very good energy resolution, a background rejection with single double blob discrimination. What else can we do? In the decay, the xenon 136 turn into a 136 barium plus, since it lost 2 electrons. So effectively measuring the production of this barium would be a unique background-free signature, since there is nothing that can mimic a double blob track plus the detection of 136 barium. How can we do it? We are experimenting. We took the technology from this single molecule fluorescence imaging, which is a technique borrowed from the chemistry Nobel Prize of 2014. So a non-fluorescent molecule with the chelation process with an incident ion can collect the ion and can start to produce light. So the first thing is to demonstrate that the first thing that we have done is that we can use the same molecule developed for calcium we can be used to see if the molecule developed for calcium can be used for the barium. So we started testing commercial molecule, and this is what we obtained on the scale of 1 micrometer. When we analyzed the light produced by a spot, after a while it was observed a single stain. The fact that this is a single stain means that it is a single molecule which stopped the fluorescence. So the first thing is that this was demonstrated in a barium salt solution. Then, of course, since we are in a high pressure ion, we have to demonstrate that this works outside a solution. And in particular for this, once we demonstrate that this is feasible, we started to test this in a dry atmosphere. So to do this, however, the new molecules were tuned computationally. So they did a computational model of a molecule, our team of chemistries, of course, not us. started to design this molecule, and they optimized it for selectivity with the barium and for sensitivity, so to give us the best light response. With this on-off molecule, it was demonstrated for the first time that this barium ion detection was possible. That this barium detection was possible in a dry environment without a solution. Here, for example, you can see this is the background part. This is the non-barium emission, while this is the emission of the molecule once the barium is added as a function of the wavelength. Here, there is also what we see at the microscope for a single molecule, which is barium chelated, so which absorbed the barium on a 7x7 micrometer. Another thing that we are testing, it's not an on-off technique, but it's a bariometric technique. So instead of having a molecule which goes on-off, our chemistry have designed also molecule which emit light in some way upon stimulation, but when this molecule chelate with a barium ion, the spectrum of emission changes significantly. Then with some filter, we have demonstrated that we can cut this region with a filter, and this lead us the observation of this barium with this technique, relying on the color shifting instead of an on-off technique. Another thing which we worked on are iridium compounds, for which the fluorescence is enhanced with the addition of barium, and they provide a response which is very short in time, so that this molecule can provide us a response of the detection of a barium, and then they kind of reset and they go back to their normal state. So the sense is that these are all things that we are experimenting, and at some point we'll find the best solution. Also because as we said, this is very difficult to do. Instead, for example, here we have done single barium imaging in 10 bar xenon gas, but for example, we have done it over a square millimeter, over a 1 millimeter square sensor. This is the usual single step function that tell us that here there was a single molecule, and this is the molecule. This is the sensor without barium. This is what we measure after barium in a 10 bar atmosphere. Okay, now we have the molecules. Perfect. We have several molecules. Now we have to move for the detection from 1 millimeter square to eventually 1 square meter of surface, which is the surface of the detector. So how do we do? We have proposed two different solutions. The first is the so-called sensor to ion approach. So what happened? It happened that we have an interaction. The electron, which are much faster in drifting, drift towards the tracking plane. The tracking plane make the imaging of the track and tell to the sensor that the track is at this XY coordinate. So then a signal goes to the sensor, and the sensor move at that position to catch the ion. So we first compute a barycenter of where the track is, and we move the sensor to where we expect the barium to arrive. Of course, this technique has present several difficulties. If, for example, moving the sensor before the ion arrives, it's not trivial. You must be very quick in computing the barycenter of the track, but then the sensor is scanned repeatedly to see if a barium interaction happened. The other way is instead the so-called ion to sensor approach. So use at this point, if you do like this, you lose the fact that you can know exactly more or less where the ions is produced. But doing like this, the sense here is to use some radio frequency carpet for to be placed here, so that when the barium arrives at the radio frequency carpet, the radio frequency carpet transport it to a very smaller surface, which is much easier to manage and to observe. This is the ion to sensor approach. As you can see here, successfully introducing the barium tagging technology would hugely improve the sensitivity from here, which are next pure xenon, next HD pure xenon, and next HD with xenon and helium for lower diffusion. This would be a game-changing technology and would lead us to reach, thanks to the fact that we are background free, would lead us to reach also 10 to the 28 years of sensitivity. And however, this is still a bit far to be reached. So these are my final remarks. We have seen the reason for why it's useful to search for a Majorana neutrino, and how the double beta decay represent a unique laboratory to search for this Majorana neutrino. So next has developed a time projection chamber electroluminescence at electroluminescence with high pressure xenon. We have seen the results of the next white NX100 and R&D development toward the next HD technology. And among all these different R&D, the barium tagging seems the most promising as a breakthrough technology for the search of for the future of the search of double beta decays. And that's all. Thank you.